Okay, so
Recording is on.
okay. Today we have the seminar of Marcos González. He is a student here in our group, and he's working on medium-induced evolution in jet quenching, and he has already one paper, I understand, and I think he's going to tell us about it.
Thank you
Okay,
for
okay, start.
the kind presentation. And as he said, I'm Marcos, and today I'm going to talk to you about multiple scatterings and energy regimes in full medium-induced gluon radiation. So this is the first time that I'm giving a seminar, so I'm sorry for all of you. Today's seminar is going to be, I'm going to display these two papers. The first paper of Carlota, Liliana, and Fabio, where they develop a numerical method to compute the fuel medium-induced gluon radiation in the BDMPS-Z framework. And the second one, that is my first paper with Carlota and Fabio, where we apply this numerical solution to see in which regions of the energy distribution multiple scatterings are important, and where just one hard scattering is enough to describe the propagation of the gluon. Okay, let me start with a very short presentation of why it's important. Why do we care about it? So when we have heavy ion collisions, like the ones that are producing LHC or RIC, we have incoming nuclei that have a very big energy, and when they collide, the energy is so high that the confined matter that are normally inside the neutrons and protons, deconfined. It's create a quark gluon plasma, and then these color particles hadronize, and we measure the final hadrons. But the important thing here is that by measuring these final hadrons, we can have information of the quark gluon plasma that was created. In other words, we have information about the confined matter. And how do we get this information? That's due to the jet quenching phenomenon. So jet quenching, it's a generic word that it's used to englobe all things that make the jets that we have inside a medium and a strongly interacting medium like quark gluon plasma. And due to interactions with this medium, jets radiate, jets produce gluons, and this has an effect on the final gluon. So here in this picture, we have two jets. The one that's up, it goes to the vacuum very fast, but the lower travels through the whole medium and goes radiating gluons every time. So when it finally comes to the vacuum, it's quenched with respect to the first one. And this quenching is due to the medium. So if we can characterize this quenching, we can have information about the medium. And the typical radiation process is the one that's here. We have a high energy parton that's produced in some point H. It has some energy. It travels through the medium. It's going colliding. At some point, radiate a gluon. The gluon itself collides with the medium. And once the gluon is released, the parton continues to radiate, continues colliding with the medium. And we usually work in the iconal approximation, and that means just that the energy of the parton is very, very high, so high that the energy that is radiated due to the emission of the gluon is negligible. And we just consider radiative energy loss. Collisions are important just for heavy quarks. And with these considerations, the propagation of the high energy parton is a Wilson line, and the propagation of the gluon is a propagator which takes in account Brownell motion in the transverse plane. And one important thing of the radiation in QCD is the LPM effect. That means that in high energy particles, when the gluon is emitted, it has associated formation time. The emission is not instantaneous. So we can have multiple collisions with the scattering centers during the time that the gluon is formed. And when that happens, the multiple collisions add coherently like one. So in practice, that means that the number of scattering centers is reduced, and this reduction of the scattering center generates a reduction of the spectrum. The spectrum is suppressed. And this LPM effect is important in high energy. But in very high energy, the gluon experiments a high one hard scattering, and this hard scattering is enough to describe the whole propagation. And with one hard scattering, we don't have coherence, we don't have the LPM effect. And finally, the last region of the spectrum is the low energy, and that's the Bethe-Heilel regime. And I'm going to tell you more things about it in the next slide. So, and just the last thing of introduction that I wanted to tell is the BDMPS-Z formalism, and I just wanted to tell you that within this framework, we can get the spectrum by resummating the multiple scatterings with the medium. And the expression is what you see in the screen. And there, the kappa is the emission kernel that has an expression by a path integral, and the P is the broadening. So the emission kernel tells us how the gluon is created by the parent parton, and the broadening tells us how the transverse momentum of the gluon changed due to the collisions with the medium. So, but this expression is known by, I don't know, 20, 25 years maybe, but it has two main problems when we want to evaluate it numerically. The first one is that the kernel is a path integral, and path integrals are very difficult to compute, both numerically or analytically. We know just a few analytical solutions. And the second one is that the first integral in time in dt prime goes up to infinity. So when we want to evaluate it numerically, it's quite difficult to do so. And so I'm going to tell you, yes. So how is, because this is very difficult to do, normally it's, we use approximations, and the two main approximations are the harmonic oscillator and the GLB. So the harmonic oscillator just use this term that it's in the exponentials, the ns times sigma, that this term encodes all the information of the media. Ns is the distribution, the density of scattering centers, the linear density, and sigma is the dipole cross section. It tells us how is the interaction due to the of the parton with the medium. So the harmonic oscillator consists on taking just the leading term in this term n times sigma. And with this, we get the path integral of a harmonic oscillator, and that's one of the few cases that we know how to solve analytically. And we have two parameters that would be the jet quenching parameter Q hat and the length of the medium L. And the second main approximation that we used in the last years is the opacity. And this opacity expansion consists on writing the dipole cross section in terms of the full Yukawa collision rate, and expanding in series the exponent, the n times sigma. And with this we get an infinite series, and the more terms we get, the more accurate. And the first term, the n equal to 1, is what is known as the GLB spectrum. So that these are the known approximations, because as I tell you, it's very difficult to get a full solution. So now let me explain you a formalism where we get a full numerical solution. And we use a different approach. So instead of trying to solve the path integral of the and then compute the spectrum, we use these Schwinger-Dyson type equations that satisfy both the kernel and the broadening. These are recursive equations. You see that you have the kernel on the left and on the right, and the same for the broadening. So if we take these equations and put it in the spectrum, first of all, we can perform analytically the integration in time, in T prime, because the dependence on time in these equations comes just in the exponentials. So we can rearrange the spectrum in the way that you can see. And as I told you, the integration in time has been performed, and now we have an integration in S, that S is the position of the scattering center. So how we are integrating now in the position of time of the scattering centers, we don't need to do the integral up to infinity, because once we are out of the medium, we don't have density of scattering center. And now this, what we do is use the fact that the kernel and the broadening satisfy these two different differential equations. And something like that was done by Carl Hunt and Gay, like 10 years ago, more or less, but they did it just for the emission rates, not for the whole spectrum. And the final relevant thing here is that the dipole cross-section can be written, as you can see, like the sum of two terms. The first one is the contribution of the of real terms, and the second one are the virtual terms. And finally, how do we compute the spectrum? We can do some algebra and rewrite the spectrum, you can see. So the only thing that we need to do to compute all the integrals is know how is the psi function. So this psi satisfies this different equation with initial condition. And in order to get the initial condition, we need to solve another differential equation. So once that we solve these two differential equations, we know the expression of psi in all of momentum and all of times, and we can perform all the integrals numerically. And this was for the full differential in KT spectrum, and we can compute now the energy distribution, and that means just integrating the momentum. So one of the assumptions that we use is that the gluons are soft, and that means that the momentum has to be smaller than the energy. So when we integrate, we put as the upper limit of the integral the energy. We can remove this limit. We can do what is called the Barrer infinite limit, and that means removing the kinematical constraint, and we integrate all over the space in momentum. And this is very easy to do because the broadening is a probability. So when we integrate all over the space, the interval is just 1. But the results of this limit has to be taken with care, because the results for a small energy are unphysical results, because as I told you, we are taking into account the kinematical constraint that has to be, because the gluons, we suppose they are soft. And finally, this is the medium modelization that we used. And for simplicity, we use the brick, but we can use any distribution for the medium. And we consider two interactions, the Yukawa potential and the hard thermal loop. And each of them has different parameters. Essentially, where in Yukawa we have N0 as parameter, in HTL the temperature, and in Yukawa we have Debye mass, and in hard thermal loop MD. And we can set a map between these two models to compare the results that they produce. The map is what is shown in the slide, and the second equation, the equation for small dipole sizes, is due to Joao and Yassin. So let me show you results for Yukawa interaction, and I remind you the expression of the Yukawa potential, and I put there the variables that I'm going to use in the plots. I'm not going to use the momentum, I'm going to use kappa, that essentially is the momentum. We use bar omega c, that it's a characteristic frequency of the medium. We use as parameter N0L, that it's more is the average number of scatterings that the gluon experiences in the propagation. And for the energy distribution, I use bar omega c again, N0L2, and now instead of kappa, we use bar R, that it's the kinematical constraint. And when we do bar R going to infinity, it's the same as removing the kinematical constraint. And so these are the results. On the left, you can see the results for the full Yukawa, the solution for the full numerical solution. And on the right, the approximation GLB n equal to 1 in opacity expansion. And as you can see, the GLB results over-predict by a lot the real distribution up to a factor 2, and the discrepancies are bigger the bigger that the kinematical constraint is. But GLB, this over-prediction comes due to the fact that GLB doesn't take into account a coherent effect, as I told you before. So in GLB, if we have the result for N0L equal to 1, if we want the result for N0L equal to 5, we multiply the whole spectrum by 5. And the whole spectrum we resummate and we take into account the coherence. But one thing that GLB does very well is that when in high energy limit, the full numerical solution goes to GLB. And this can be seen better here in this plot. In the left, we have the same as before, the energy distribution for different length mediums. And on the right is the same, but it's in log scale. And as you can see, for very high energies, the GLB resultant is very, very close to the full numerical solution. Oh, I didn't tell you, the solid line is the full result and the dashed dot line is the GLB. So as you can see, for high energies, we can just use GLB and we don't need to perform a full numerical solution. And then these are the results for the differential in KT spectrum, and the same as before. When we go for very high energies or very high transverse momentum, GLB and Yukawa and the full solution gave the same result. But when we go to lower energy or momentum, the results are different. And the results, if you see, these are the results for N0L equal to 1. So in N0L equal to 1, we already see discrepancies. If we move to N0L equal to 5, the discrepancies are bigger. And now, very fast, I'm going to show you the results for the HTL in order to see you that we can use this method with any collision rate that we want to use. So here we have the collision rate and the variables that I'm going to use in plots that are the same as before, but now with a subscript h. The momentum, characteristic frequency, and now we use TL instead of N0L. And for the energy distribution, the same. We use bar R H instead of bar. The results for any distribution are more or less the same that with Yukawa. And here is the comparison between Yukawa and HTL for the differential spectrum. And as you can see, when we go for high energies or high momentums, both collision rates give the same result. But when we go to small energies or small momentums, the behavior are completely different. And as you can see in the down row that the HTL potential gives some dumps that are not present in Yukawa collision rate. So that was the first part of the seminar, and now I'm going to explain the second paper. That is the paper where we focus on the energy spectrum to see where multiple scatterings are important to describe the energy distribution. So first of all, let me explain what I mean by energy regimes. So as I told you before, the gluons have an extent formation time. This formation time is proportional to the energy, and it's it's proportional to the energy divided by the momentum. So if the energy is bigger than an energy that it's omega c, I'm not going to write the expression. It's not relevant for what I'm going to tell. If the energy is bigger than this, the formation time of the gluon would be bigger than the length of the medium. But we don't want that. We want the gluon to be created inside the medium. So the only solution is that the momentum has to be big too. It has to be very big compared with the usual momentum that the medium transfers to the gluon. And when this transmission of momentum is very high, it's what we call a rare scattering, a hard scattering. And when that happens, this one hard scattering is enough to describe the propagation. So the n equal to 1 opacity expansion is enough to describe the redistribution, and that's what we saw on the plots where at high energies GLB work really well. On the opposite limit, if the energy is smaller than energy omega beta high, then the formation time would be smaller than lambda. Lambda is the mean free path, is the average distance between scattering centers. So if the formation time is smaller than the distance between scattering centers, we can't have two or more scatterings. And it's what's called the beta-Halley regime. And in a few slides, I'm going to see if this approximation works well or not. So due to these two facts, we expect that in the for energies between omega beta Halley and omega c, multiple scatterings are essential to describe the propagation. So formalism like harmonic oscillator and extensions should work really well. So first of all, let's take care of the asymptotic limits of high energy and small energy. So let's take the spectrum. This is the spectrum that I showed before, but as I told you before, I integrate the whole broadening up to infinity. So the integral is just 1, and that's how we take care of broadening. And now with this equation, we use the Schwinger-Dyson equation that I showed you for the kernel, that is the second line. And if we take this equation, then we can perform the opacity expansion. Then the first term in the Schwinger-Dyson equation is just the vacuum contribution. We don't care about it. We just care about medium-induced emissions. So if you take the second term and put it in the spectrum, we get the first term that it shows with the n equal to 1. And that is GLB, exactly GLB. Carlotta, Lilian, and Fabio checked that in their paper. If we use the second term, we put the second term of the Schwinger-Dyson equation, we get what it's there, and now it's essentially the GLB result time another one. So let's take a look in the P integration of this second term. So if we use the expression for the dipole cross section that I used before, we can put the P integration in terms of the collision rate, and the contribution of the virtual terms it has a delta, so the integral is very easy to do, and we have just the L, and the contribution of real terms has this phase. Is the P times the exponential. So what happens in the asymptotic limit? If the energy is really high, the phase goes to 1 because the energy is really high. So P squared divided by omega is 0, and the exponential of 0 is 1. And the integral of P integrated in P times the collision rate is 0 by construction of the potential. The potential has azimuthal symmetry. So for high energies, this term doesn't contribute. We just have the contribution of virtual terms. And what happens in the opposite limit for small energies? For small energies, when we integrate over P, this phase oscillates very fast. So when we perform the integration over P, it doesn't contribute. So basically, we can neglect the term with P. And that's what is written in the second equation. So we just have to perform the integration of the potential, and we use M squared as a cutoff in case the potential has the infrared divergence. And for large energies, this sigma, that's the integral of the potential, it's what is written there. So if I remind you that sigma, it's basically the last line of the n equal to 2 term. So what we have is that the n equal to 2 term is the n equal to 1 multiplied by sigma, more or less. And sigma has a power 1 over omega. So that means that the n equal to 2 is suppressed by one more power of 1 over omega. And that's the reason why GLB works so well, because when we go to energies up to infinity, n equal to 2 is negligible against n equal to 1, and the same happens for higher terms in the expansions. And what happens now with the small energy regime? So I write the expression of the n equal to 2 term. I didn't do anything with it yet. And now if we compute the next term in the series, what we would get would be, and we resummate all of them, we would get the series expansion of the exponential. So these contributions exponentiate. And what we get is for the resumed spectrum is the n equal to 1 opacity expansion, the GLB, times an exponential. And it's an exponential that comes due to the virtual terms of the dipole cross section. So physically, what we have here is that the spectrum for the low energies is the GLB n equal to 1. So we have one scattering times a probability of have no more scatterings. And that's something important that we didn't know till we derived this equation. We just thought that GLB should work more or less well for very, very small energies, because we should have just one scattering. But with this, what we see is that this picture of have just one scattering works for the real terms of the potential, but for the virtual contributions are unconstrained. So when we take the virtual contributions into account, they exponentiate and give us this. And here are numerical results to see if these approximations work well or not. Here, the solid line is the full solution. The dotted line is the spectrum that we just derived, the low energy spectrum. And the dashed dotted line is GLB. So as you can see, both for Yukawa and HTL, GLB predicts by a lot, over predicts by a lot. And when we go to energies small enough, the small energy spectrum is very close to the full numerical space. So now that the limits of the spectrum are already taken into account, let's move on to the multiple scattering regime. So the natural comparison to do would be with harmonic oscillator, but harmonic oscillator has a problem. That's if we, in harmonic oscillator approximation, we have the Q hat, the jet quenching parameter, but this Q hat depends on a cutoff. When we perform this integral over Q, we have to put a cutoff, an upper cutoff. So the correspondence between the parameters of our formalism and the harmonic oscillator would depend on this cutoff. So we just could perform qualitative comparisons. But recently, Yassin came with an idea, what he called improved opacity expansion. And the idea is the next one. Take the harmonic oscillator approximation and decompose this V of R in two terms. So the first one is simply the harmonic oscillator term. It's R squared times a constant. And by doing so, the second one can be treated as a perturbation and use the formalism of perturbation and do a expansion series around the harmonic oscillator that it's a solution that we know. And here this Q square is the matching parameter, and it's of order this Q square C that it's defined through this transversal equation. Then if with this formalism we compute the leading order term, where we just use the harmonic oscillator, we recover the solution that all we know. And if we compute the next leading order in perturbation series, we get what is there. And these are the results that Joao and Yasin got in their recent paper. So like it's written there, the spectrum seems to depend in three different variables. We have Q hat 0, the jet quenching parameter, the first jet quenching parameter, because as you can see, the jet quenching parameter now depends on the scale on Q squared. We have a mu star, that is essentially the biomass. And we have the length of the medium in the interval of the next leading order term and in the cosine in the harmonic oscillator. But what Carlota and Fabio saw is that if we define these two frequencies, the omega C and the omega beta Heiler, they are what I wrote before for explaining the energy regimes. Then if we define these energies this way, the spectrum can be put just as function of two variables instead of three. And these two variables are chi and x hat. And chi, if you see, is omega C over omega beta Heiler. So it's more or less how big the multiple scattering region is. The bigger that's chi, the bigger the region will we have. So these are just the expressions that we got using these two variables instead of the variables of the original paper. And as you can see here, we have one problem is that we have a dependence on A. I remind you, A is just a parameter of order 1 that puts us the scale. So what Yasin and Joao claim is that this dependence on A is strong in both in harmonic oscillator and next leading order, but when we do the sum of the both of them, the dependence is not as strong. So we check that, and here we have plot. In the dotted line is just the harmonic oscillator term, and the dashed line is the sum of harmonic oscillator and the next leading order correct. So as you can see here, for small chi, this formalism doesn't work very well. But once that chi is big enough, the dependence on A is very, very small. And chi is essentially N0L. So we saw that for chi approx to 14, the formalism start to work well. And that is more or less N0L. So as the dependence is low in A, we set A to 1 for the rest of the paper. So now that we have expressions for both for the full numerical results and for this improved opacity expansion, we perform a comparison with the, both of them, of both of them. And for simplicity, we just use the Yukawa collision rate, and that's because, as I told you, we are interested in energies bigger than omega beta Heiler. And for the energies that we are taking in count, both Yukawa and HTL gives the same result. For big energies, Yukawa and HTL, we saw it in the plots, they gave the same result. And as you can see, here we have GLB, the full result, and the improved opacity expansion. GLB overpredicts a lot, so the full result. So that means that multiple scatterings are of importance. And the improved opacity expansion gives a very good approximation to the full numerical result. Here we use the map that's there to go from variables of the full numerical solution to improve opacity expansion. And the range in energies is set as the lower limit is more or less 10 times the omega beta higher. And that's because if the energies is lower than that, the formalism of improve opacity expansion fails. Okay, so now that's the final part of the seminar, and it's the last thing that we did in the paper, and is now compute the emission rates of the spectrum. So what's the emission rate? Basically, the emission rate is defined as the derivative of the spectrum with respect to L. Sometimes interpreted as the probability of the parent parton to produce a gluon at a given time. That it's somehow imprecise. As I told you, the gluons have an extent formation time. The emission is not instantaneous. But if the emission time is much smaller than the median length, this approximation works really well. So if we want to compute the emission rates for the field result, the whole dependence in L was just in the upper limit of the integral of the position of the scattering. So what we have to do is not perform the last integral. And for the improved opacity expansion, we have analytic formulas, so we just derive it. And instead of use L as time parameter, we use K. And these are the results that we got for the improved opacity expansion. And here is the comparison between the two formulas. So as you can see, when chi is big enough, the emission rate goes to a constant value. And this constant value for the full numerical solution is the same as the AU result. And this was checked by, we checked this in the equation. It's not just a numerical fact. And we see that the improved opacity expansion goes to a constant value, but it's not the same value as our full numerical result. And the bigger the energy of the gluon, the smaller the discrepancy between the improved opacity expansion and full numerical solution. And here we see also that for small values of chi, the improved opacity expansion doesn't work very well. And you can see that the emission rate has some unphysical oscillations that are not in the full numerical system. So the bigger that chi and the bigger that it's x, bar x, fat x, or what's the same, the bigger that it's N0L or omega, the better the agreement between improved opacity expansion and the full numerical. And this is a plot that summarizes more or less this second paper. And so here, what we have is for a chosen value of N0L, the energy distribution, and we have the full numerical solution, the improved opacity expansion, GLB n equal to 1 in opacity, and our low omega limit. So we see that, first of all, for very, very big energies, GLB is enough. We don't need opacity expansion, improve opacity expansion, we don't need full numerical solution. In the opposite limit, for energies very small, the low omega limit predicts the full numerical, it's the same as the full numerical solution. And then we have the region of multiple scatterings, and so when GLB starts to fail, we can use the improved opacity expansion, but this improved opacity expansion doesn't match the small omega limit. We have a window of over from 3 times omega beta Phi to 10 times omega beta Phi. There are no theoretical approximation that give us a result close enough to the full numerical solution. And this is the slide, the conclusions. The conclusions are that we developed, when I say we, I mean Carlota, Fabio, and Liliana, developed a method to evaluate medium-induced gluon spectrum with resummation of all scatterings. We can use this setup with a different realistic parton medium interaction model. We use it with Yukawa and HTL. And we didn't do it yet, but we can use any profile for the medium. That's something really important too. And our framework is valid for phenomenological applications. And as I just showed, it's also valid to study the validity of usual employed analytical approximation. Using this full numerical solution, we saw if GLB is good enough, if where multiple scatterings are important, and all of that. And finally, the main contribution of the second paper is that we obtained a low energy asymptotic limit of the full resume. And that's all I wanted to tell, and thank you for your attention.
Thank you very much. Any questions?
So you can go to slide 28.
Okay.
The small omega.
Yeah.
Yeah. So you neglect so if you go to the previous one,
Yep.
you argue that you neglected the phases
Yes.
because you have the omega in the exponent, and then this oscillates a lot, and then you get only to the virtual terms.
Yes.
Okay, but so if you go now to the next slide. But so in this small omega approximation, you still keep the phases in the integral. Why is it so? Sorry, I think I didn't pay attention in the paper to this.
I think that's quite difficult for me. If I can get help of Fabio, Fabio was the one that derived this expression, so I understood more.
No, it's a little tricky. You cannot get rid of all the phases because then you have a divergence in one of the integrals. So
well, actually, the first phase, the one that you see. Can you go to the previous slide?
Yes.
This one, yeah, the n equal 1. If you get rid of that phase, you have a result that is purely imaginary, and you have to take the real part. So you don't have GLB, so you always have to keep the first phase.
Why is it? Because everything is real in the way you write the things.
yes.
So the first phase needs to be there if you want to have at least GLB.
Well, but I guess that this means that you have to this oscillates, and you have to take the imaginary part. Doesn't mean that you have the phase. I mean, of course, for GLB you have the phase because this phase is the one that gives you the coherence, etc.
Yeah,
but you argue that for small omega the phase oscillates a lot, and then so I was expecting to have better Heitler, which is basically this thing without the phase. No. Better Heitler.
I mean, what you can do at that point is you have to be careful because it's true that for if omega is small, everything oscillates, but p can also be small. You integrate all p's, right? So what we're saying is that that phase, we leave it there because we know that phase is very important to get the result. If p, so it's only the low p region which is going to be important. So actually, you can just say that you can just perform that integral up to some value of p, and then.
But this is the same phase you are neglecting in the other place.
No, in the other places, I mean that's the easy explanation is to say that you neglect it. Actually, you have to keep a little bit of the phase. And that's why, if you go to the following slide, that's why we say that you have this sigma in which you don't integrate the potential over the full space. You have to cut then like a little circle. And there's a little disk that you don't include in that integration. The thing is that part is only relevant if the potential is singular. Otherwise, that contribution is very small. It doesn't matter if you integrate over the full space or not. So what I'm saying is that you have to keep the phases as long as they are regulating a singularity. Otherwise, you can get rid of them. So the one in the n=1 term, you have to keep it because it regulates the singularity. And that means that any other phase that is of the same order, you have to keep also. But then, in the final result, if the potential is not singular at 0, it doesn't really matter if you kept those small pieces. You can just throw them away, and numerically the difference is negligible.
But if the effect of the phase is just to provide a cutoff,
Yes.
provide a cutoff, why can't you play the same game in the present? I mean, well,
can.
yeah, because it's a difference. I mean, it's L minus Q dot the phase, isn't it? Q times the phase.
Yeah, what you're doing is that you can neglect that term always, that P squared is is not very similar to L squared. That's what you're doing, actually. That's why he says that this. So yes, if omega goes to 0, that space oscillates, except if P squared is very similar to L squared.
Well, but yeah, this is what you normally do. This is why you fix P equals L.
Yeah.
And also when S prime is equal to T.
Yeah.
And this means
Yeah, that's why for the large omega has this mu squared L omega defined from that.
Well, I guess you're correct. I mean, I understand the point that the phase regulates singularity. This is the whole thing with BDMPS and GLB, that they are not divergent in the infrared and the collinear. But there is other ways of regulating a singularity. So you're keeping a phase in one place and not in the other. That's, I guess it's okay, but
No, I mean, actually, the way that we do it, we keep the phase everywhere where the phases are of the same order.
where the phases are the same order.
It's just that if there's no extra singularity to regulate, it doesn't really matter if you keep the phase or not.
No, I understand what you said, but yeah, okay, good. Thank you, Mark.
Welcome.
Okay. Any more questions? And maybe
I have a question.
go ahead.
Yes. Can you? I mean, this is a very simple question, but can you explain if so in the rate calculation, should there be any difference to what you compute and the computation by Gale and so the paper that you cite on the rate equation, on the rate, sorry, or should this be the same in the end?
And sorry, can you repeat? I didn't understand you.
Okay, sorry. So if you go to the, I don't know what is the slide, sorry, but this is the slide where you compute the rate.
The rate, okay. Yes.
So my question is very simple: should this result be the same as the one that is in the paper by Gale and Caron, or where they could just compute the rate essentially using the same techniques that you are using, or should this, or is there any difference?
If there are any difference between this and the paper of who?
Gale and
It's the same, no?
Well, so,
Yes.
so in their paper, they never compute the broadening. They always integrate.
But this is without broadening.
But yeah, and this is without broadening. But yes, if you take the
Yeah, the answer is yes.
yes.
The answer is yes. This is the same as as what they did in that paper. They actually do something that is a little bit more general because they have a finite fraction of energy. We can also do that. For us, it's trivial to put it, but since we were always in the sublimit, we did it in the sublimit also. But it's the same. At this level, it's the same.
Yeah.
Oh, okay. I just wanted to know if it was the same or not. Okay, thanks.
Okay, so if we don't have any more questions, I think we can finish here. We can thank the speaker again.
No, primero salgo.